Today we have to discuss the electrical and magnetic properties of solids. Electrical properties. There are three types of solids: conductors, semiconductors, and insulators. Conductors, there are conductivities ranging from 10 raised to 4 to 10 raised to 7, ohm raised to -1, meter raised to -1. In the case of semiconductors, conductivity is ranging from 10 raised to -6 to 10 raised to -4, ohm raised to -1, meter raised to -1. In the case of insulators, conductivity is ranging from 10 raised to -20 to 10 raised to -10, ohm raised to -1, meter raised to -1. In order to explain these properties of solids, there are different theories. One of the important theories is band theory. Band theory is based on molecular orbital theory. Here you can see the molecular orbitals of lithium. Only one lithium, it is the atomic orbital. Li2, if there are two lithium atoms in a crystal lattice, if there are two lithium atoms, we can consider only the outermost electron, which is the outermost electron of lithium, 1s2, 2s1. Therefore, 2s1 is the outermost electron of lithium, or 2s is the outermost orbital. So in the case of lithium, when two atoms combines, the two atomic orbitals, that is 2s orbitals of two lithium atoms, undergo linear combination to form a bonding molecular orbital and an antibonding molecular orbital. Total how many electrons in the outermost shell? 2 electrons. One in one of the lithium atom, one in the other lithium atom. Therefore, these 2 electrons will enter into the molecular orbital. Bonding molecular orbital. Antibonding molecular orbital will be vacant. In the case of Li3, how many atomic orbitals are combining? 3 atomic orbitals. 3 2s orbitals are combining, and as a result, you will get 3 molecular orbitals. Out of these 3 molecular orbitals, 2 are filled, and this antibonding molecular orbital will be vacant. If there are 4 lithium atoms, 2 bonding molecular orbitals and 2 antibonding molecular orbitals will form. Only the bonding molecular orbitals will be filled. In case of n lithium atoms, we can see n atomic orbitals will combine, therefore n molecular orbitals will form. As the number of molecular orbitals increases, it is very difficult to find out the difference in the energy of molecular orbitals. The energy levels will be very close to each other. That means that we can consider it as a continuous energy band. So you will get 2 bands. One will be completely occupied. We will name it as valence band, and the other will be empty or vacant. But if the bands are very close to each other, promotion of electrons from valence band to conduction band is possible. Since conduction band is free, vacant, if there are some electrons in the conduction band, they are free to move from one side to the other side of the solid. Therefore, these electrons, due to the movement of these electrons, electrical conductance is possible. That is clearly explained. The conductance of conductors, semiconductors, and insulators are clearly explained here. In this diagram, it is very clear. You can see it is a case of lithium, partially filled band. This is a single band, half of it is filled. And we can consider it as the conduction band and it as the valence band. Since there is no energy gap between conduction band and valence band, promotion of electron from valence band to conduction band is possible. If there are electrons in the conduction band, electrical conductance is possible. It is another case. Here two different bands, but these two energy bands are overlapping each other. And promotion of electron from valence band to conduction band also possible here. And in this case, you can see there is a large energy gap between valence band and conduction band. Therefore, promotion of electron from valence band to conduction band not possible. So, such solids are insulators. There is no conduction. There is no electron in the conduction band. There is a large energy gap. So, promotion of electron from valence band to conduction band not possible. And in this case, there is a small energy gap between valence band and conduction band. So, promotion of electron from valence band to conduction band is possible, but it is not possible as in the case of conductors. Here the bands are very close to each other, but here there is a small gap. Therefore, only a few number of electrons will be promoted to the conduction band or empty band. So such solids are known as semiconductors. So here a clear explanation is given for conductor, semiconductor and insulators. The energy gap between valence band and conduction band is very small, or the two bands are overlapped. So promotion of electron from valence band to conduction band occurs. In semiconductors, intrinsic means that substance itself is a semiconductor. The semiconductance is not due to the introduction of an external particle. That substance itself is a semiconductor. Such semiconductors are intrinsic semiconductors. The energy gap between valence band and conduction band is small. So, a few electrons can jump into the conduction band. In insulators, large energy gap. So, promotion of electron to conduction band is impossible. Doping. We already mentioned intrinsic semiconductors are semiconductors by itself without the introduction of any foreign particle. These intrinsic semiconductors, its conductance are too low to be of practical use. Therefore, the conductivity of intrinsic semiconductors increased by adding appropriate amount of suitable impurity. This process is known as doping. The conductance of semiconductors can be increased by the introduction of calculated quantities of suitable impurities. That process is known as doping. Here we can consider semiconductors such as group 14 elements. You know, silicon, germanium, they are semiconductors, intrinsic semiconductors. Their conductance that is too low to use in practical purpose. Therefore, we will dope it with the group 15 elements. Doping means introduction of impurity to the crystal lattice. So we will introduce group 15 element to group 14 element. Then what happens? Group 14 elements have 4 electrons in their outermost shell, and group 15 elements have 5 electrons in their outermost shell. 4 electrons will be shared and the 5th electron will be free. That can be considered as a delocalized electron. Because of the presence of this delocalized electron, the conductivity will increase. So here Group 14 elements are doped with the group 15 elements such as phosphorus or arsenic. As a result, free electrons are produced in the crystal lattice. Therefore, conductivity increases. If the increase in conductivity is due to free electron, we will call it as N-type semiconductor. If group 14 elements are doped with the group 13 elements like boron or aluminum or gallium, which has only 3 electrons in the outermost shell. So all the 3 electrons will be paired, but for the 4th electron, there is no other electron for pairing. Therefore, there will be a hole or a vacancy of electron. This hole can move from one end of the solid to the other end, and it also will help in the conductance. That means shifting of electron to the hole, then a new hole will be created, another electron will shift to that hole, another new hole will be created. In that way, hole can move from one point to the other. And because of this movement of this hole, conductance of the semiconductor will be increased, or conductance of group 40 elements will be increased. And it is known as P-type semiconductor, conductance due to hole, therefore P-type semiconductor. Now group 14 elements are semiconductors. So here 13 and 15, what is the average? 14. 12 and 16, what is the average? 14. So certain studies are conducted on compounds formed in between group 13, group 15 elements and group 12 and group 6 elements, and identified wonderful metallic character in such compounds. They are usually known as 13-15 or 12-16 semiconductors. Typical compounds of group 13 and 15 are IN, SB, ALP, and GAS. Indium antimonide, aluminum phosphide, and gallium arsenide. Gallium arsenide semiconductor have very fast response and have revolutionized the design of semiconductor devices. So such a research identified the semiconductor property of such compounds. For example, gallium arsenide, that is a very good semiconductor which has fast responses. And in the case of 12-16, zinc sulfide, a usual compound, zinc sulfide, cadmium sulfide, cadmium selenide, and mercuric telluride. All these are examples of group 12-16 compounds. They also have semiconductor properties. So these compounds are usually known as 13-15 or 12-16 semiconductors. You have to remember some examples. And the last portion of this chapter, that is magnetic property. Before magnetic properties, electric properties of metal oxides. In the case of metal oxides also have some metallic properties, that means electrical conductance. They are also showing electrical conductance. Here you can see the examples of some metal oxides. Titanium oxide, chromium dioxide, and rhenium trioxide. These 3 oxides behave like metals. If you consider rhenium oxide ReO3, that is behaving like copper in its conductance and appearance. Its appearance like copper, and its conductance also very close to the conductance of copper. If you analyze certain other oxides such as oxides of vanadium, VO, VO2, VO3. In this case, they show metallic or insulating properties depending on the temperature. As the temperature changes, their conductance changes. TiO3, titanium trioxide, another example, which also has changes in its conductance with the temperature. Now we are going to the last topic, that is magnetic properties. And what are the applications of N-type and P-type semiconductors? You can see to make diodes, transistors, amplifiers, and rectifiers. You are studying about these instruments in physics. Magnetic properties, paramagnetism. What is paramagnetism? Weak attraction in the magnetic field. If you bring this substance to a magnetic field, that will change it to a magnet that will be attracted in the magnetic field. For this, unpaired electrons are required. If there is unpaired electron in a compound or in an element, it will behave as paramagnetic substance. Examples: O2, Cu2+, Fe3+, Cr3+. Substances which are weakly attracted by a magnetic field. Next, diamagnetism. Diamagnetic substances are weakly repelled by magnetic field. For example, if you bring a strong magnet into such a compound, that will be repelled. If you bring it near to water, you can see water will be repelled in the magnetic field. What is the reason? Water is a diamagnetic substance. So diamagnetic substances are having completely filled orbitals. There is no unpaired electron. Completely filled orbitals. No unpaired electrons. Examples: H2O, NaCl, and benzene. Ferromagnetism. Ferromagnetic substances are strongly attracted in a magnetic field. If you bring such a substance into a magnetic field, that will be converted to permanent magnets. That means that will behave as magnets even in the absence of magnetic field. What is the reason for this? The reason in the solid state, the metal ions of ferromagnetic substance are grouped together into small regions called domains. Each domain has a magnetic moment. The magnetic moments of these domains will align in the same direction as the applied magnetic field. That is the reason. This figure represents the alignment of magnetic moments of domains in the same direction. Therefore, they are strongly magnetic. Examples: iron, cobalt, nickel, gadolinium, and CrO2. Next, antiferromagnetism. In antiferromagnetism, the substances are really magnetic, or which has domains. But we cannot observe magnetic moment in the case of antiferromagnetic substance. The reason, in the magnetic field, magnetic moments of domains will align exactly in the opposite direction. Here you can see in the figure, one is in the upward direction, other in the opposite direction. So magnetic moments will cancel each other. So the net magnetic moment will be 0. Example: manganese oxide. Now, ferrimagnetism. Ferrimagnetic substances are magnetic in nature, but their magnetic moments will be less than that is expected. That is due to the irregular alignment of domains, magnetic moments of the domains. They are weakly attracted by magnetic field as compared to ferromagnetic substance. Ferrimagnetism is observed when the magnetic moments of the domains in the substance are aligned in parallel and anti-parallel direction in unequal numbers. Irregular alignment. Examples: magnetites and ferrites, Fe3O4, magnetite. Ferrites, MgFe2O4, ZnFe2O4, etc. By this, the chapter is over, and in the Google Classroom, I will give you an assignment. So all of you study well this chapter. Shortly you can expect an examination. Okay.